promises to open a vast energy and material wealth of the solar system to people remaining on the Earth and to protect them from asteroid impact. Recent scientific and engineering progress, much of it due to people in this room now, promise to allow space settlement to begin in earnest within the next couple of decades. We will need new technologies to allow settlement beyond our Earth, and our goal is to pursue those. It's wonderful and gratifying to see such a capable and distinguished group of people here. And now I would like to introduce Jeff Greason, the CEO of XCOR Aerospace, a member of the Augustine Committee, and Senior Advisor to Space Studies Institute.
Let me start by repeating Lee's welcome. This is an endeavor and an enterprise that I have believed in as long as I can remember. I now find myself in the rocket business. It's not a business I ever wanted to be in. I'm not in it because I love, making smoke and fire. I'm not even in it because I love space transportation. I just wanted to ride. I needed a way to get places out there that I thought there were interesting, important things to do. And I grew up believing in a vision of all the wonderful things we would do in space with that magical machine, the space shuttle. Dropped the price of transportation to orbit to $100 a pound and was flying every week. You remember those days. And it didn't happen, and I got tired of waiting. So now I'm in the rocket business. But there simply is no point in going almost any place just to go. You have to have some reason for going. You have to have something to do when you get there. If you're going for the purpose of exploring and you have no thought in your head of what you're going to do with the things that you find or with the new lands that you've discovered, what's the point? And when people bemoan how members of the public are not as engaged or enthusiastic as perhaps they once were about space exploration, I think it's very simply that. They are not stupid. They have seen that there was no point. But there can be a point. There should have been a point. And there still is a point. It simply has not been the focus of what the exploration endeavor that's funded by our taxpayer-funded activity has been. And the point is to go live there. Now here we sit at the dawn of the 21st century, with centuries of the Renaissance and the Industrial Revolution behind us, with powers at our fingertips that our ancestors would have thought magical. With a click of a gods, and might as well get good at it. So are we celebrating? Are we all happy? Are we proud of what we've done? As a civilization, I don't see that. I see us almost ashamed of what we've done. I see us embarrassed to talk about the things that I just said about how far we've come and about how far we still have to go. I see us almost cowering and unwilling to take on the responsibility of wielding the power that we have created. That's a symptom. The disease behind it is the closing of the frontier. That great period I talked about sparked with the Renaissance, with the contact with new cultures, with the discovery of new knowledge, with the trading to new regions. New things bring new problems. They also bring new opportunities. That brings the opportunity to change how you do things. When you live in a society where you think we've got all there is, it's not going to get any better, people become obsessed with holding on to what they've got. Change is always a threat to people who have something now. If you can't create new things or find new things or bring new things, if you have to get something by taking it away from something else. And that's what gives rise, in my opinion, to so many of the pressing errors in the culture today, to the feeling among some scientists that we've made all the big discoveries, to the feeling among people who Meanwhile, we sit at the edge of an ocean full of every resource we could want, all the space you could wish, energy pouring through it in quantities we can barely imagine. We are sitting here squabbling over scraps while the banquet is out there limitless and waiting for us. We are sitting here worrying about whether or not we might unintentionally have some impact on the Earth's climate or environment, while Mars sits there begging for us to go have an impact on its climate and environment, to warm it just a few degrees. With the light of recent discoveries and knowledge, it looks like timeline was more prescient than we could ever have guessed. The moon is not sterile, it is not dry, it is going to support a great culture. It is going to be the economic and transportation crossroads of the inner solar system, and it's all going to rest in the backs of the ice miners. It is time for us to stretch out our hand and take what the universe is begging to give us. And that dream, comes down to us from a legacy in large part of a man named Jerry O'Neill, which became embodied in the Space Studies Institute. And one of the turning points in my life that got me in this crazy business, doing these crazy things, is picking up a book when I was in junior high school called Colonies in Space by T.A. Heppenheimer. And I can still see very clearly the beautiful illustrations in that book of what those space colonies might have looked like. And yes, we can look back now with 30 years more experience and see that some of the technical ideas might have not been quite right, and some of the assumptions might have not been quite right, and some of the economic ideas are a little naive. But that doesn't matter any more than it matters that we look back at Isaac Newton and go, yeah, there were a few things he didn't get quite right. Okay, that's not the point. Somebody had to be the first to stand up and think about how space would be part of the economic system of an ever-expanding humanity. To realize that colonists, people have written about colonies and outposts in space since the early days of science fiction. But somebody had to be the first one to stand up and say, okay, don't these people have jobs? Don't they have something to do that causes them to be there? Don't they have, this is my words, not his, some kind of cash crop that they can use to pay for the few imports that they need, while they meet most of their material resources by growing and mining things locally? Doesn't it work like every other colonization effort that's gone on since we walked out of Africa? I think it does. And Jerry O'Neill was the one who stood up and said that. To steal a phrase from a good friend of mine, Rick Hudson, we are all Jerry's kids. And it's a great pleasure for me and privilege for me to be here to welcome you, to pick up after a pause that effort, and to begin integrating all the new knowledge that we gained, the promising advances in the onset of commercial space transportation that have gone on, and start thinking afresh about how are we going to actually get out there, make it pay, leave this earth with people who will not come back, and will go on to be the beginnings of the next great wave of our human adventure. Thank you.
Hudson. Gary, as you may know, is a brilliant man. His brilliance is not his distinguishing characteristic in my view. His distinguishing characteristic is courage and perseverance. He had the courage to say, I think I can build a spaceship that can lower the cost of space transportation. And I think Gary is right. He, given adequate support, could have done that a while ago. He, I think, opened the door for a lot of other people to think the same way and have the courage to follow in his footsteps. So he is the chair of the next session. Gary?
Thanks, Lee. I'd really like to thank you and Robin for providing the space manufacturing conferences. It's a little appalling to me, I don't know if disappointing is the right word, sobering, that the last time I chaired a session at one of these conferences was 3 decades ago. Yeah, I think it's long overdue that we honor Jerry O'Neill's legacy by beginning afresh with a new series of these efforts. So we're going to start this session on space transportation with 3 speakers. I'm going to lead off and talk to you a little bit about Earth's orbit space transportation. I'll be followed by Bienhoff of Boeing, who will talk about in-space technologies and transportation systems. And he'll be followed by Joe Carroll, who's going to talk about various applications of tethers in Earth orbit, with an interesting little segue of artificial gravity and tethers that didn't fit in any session. I'd like to hold the questions and answers until the end, where we're going to do a panel, and we'll be joined also by John Goff of alt.space machines at that time, who could do Dallas's presentation as well. So with that, our problem is getting off the ground. Next one. Oh. Okay, so why is this a problem? There's a little bit of preaching to the choir here, and a lot of things you already know, but perhaps some of you don't, and so it's worthwhile to review. The cost of access to low Earth orbit constrains everything we do in space. Everything. And as Robert Heinlein and others have pointed out, once you're in orbit, you're halfway to anywhere else. So I'll take a fairly parochial view as a space transportation systems designer and say nothing else matters as much as low-cost access to space. And you only get low cost by having routine and reliable access. So what's the biggest challenge, or your group of challenges? Well, from my perspective, it is not technology. I'm a technologist. I love talking about technology. You get 3 engineers around the table, we'll come up with 5 different solutions for you. The technologies are life. It's enjoyable. It's part of why we do this. But the challenge has been, and will continue to be, the market demand. The pull that creates that traffic model. From that flows issues of financing. And then one of my pet peeves is naive regulation of the industry. I'm pretty much alone, I think, in that pet peeve, unless you get it. But now I'll speak to it a little bit later. Okay, so it's not technology. It's not destinations. This is an extremely frustrating part of the constellation argument. It's not heavy lift. We don't need heavy lift. Exactly what that means. We need traffic. Okay, and we need tonnage in orbit. It doesn't necessarily have to be in 100-ton segments. This building was built by trucks that take 10 tons at a time, and a lot of hands. We don't need enabling legislation. We don't need spaceports per se. Politicians love spaceports because they're infrastructure. Okay, and, you have concrete, lighting poles, and buildings, and jobs. Historically, we've had a problem with NASA opposition. That's no longer the concern. The sea change is a rather active phrase. It's overused. We've had a sea change. The times have, in fact, changed. The problem is Congress hasn't caught up. So why is launch expensive? Well, first, it's sort of obvious we throw the launch vehicles away. And secondly, we fly them only once. So you might say this is redundant. But in fact, there are 2 separate issues. By throwing the lock yourself into high costs for the same reason that if you used an aircraft once and threw it away, it would be a high cost proposition to cross the country. The flying only ones reduces our reliability. And that's really what drives things like safety. And also drives the learning curve in development. If every time you fly is the first time you fly, there's obviously a problem. And so, bottom line is we don't fly often enough, and we can't amortize our overhead development costs. So what's been tried? Tom Wolfe, in his great book, The Right Stuff, talks about a test pilot who's in trouble and says, I tried A, I tried B, I tried C, calling down to the ground. So what's been tried? Everything's been tried. Right. We've looked at reusables, partially reusables, rebuildable, salvageable rockets, some used to call them expendables. We've looked at one stage. That's my take on that. We've looked at multiple stages. We've looked at various forms of launching, various forms of propulsion, and various forms of financing. So what's work? Nothing. I mean, bottom line is nothing has worked. Because if we're talking about true, real cost breakthroughs, which means 55 or 10 times propellant cost, about what airlines and executive jets fly, we're not ever anywhere close to the breakthrough of low-cost, inexpensive space transportation. And the bottom line for me is it's the standing army. This is a phrase that Max again coined, which I stole him. And to borrow a political phrase, this political era or time, it's the standing army, stupid. It's the number of people. So you've got companies like Carroll, Orbital, and now SpaceX, who have developed new launch vehicles, focused on largely commercial solutions. Yet, none of them have fundamentally reduced the cost of access to space, sufficient to expand the market. So this chart, it's a little hard, I'm sure, for you to read, but the message from it, Dave Andrews graciously provided this. He did a study, I think it's probably 10, 12 years ago, called the Future Space, or the Future Commercial Space Study for NASA. And in fact, I think this is something that Lori Carter got funded a long time ago, so Lori's contribution to this field goes back in a very great way. And what he shows here is this is the cost. This is the total market cost, and this is the launch rate, and this is dollars per pound. And so this is where we are currently with ELDs. This is where we have to go for true elasticity of the marketplace to build the market that's necessary to see widespread commercial applications happen in space. This is the relevant curve. That's the money curve right there. Okay, so currently, there's going to be $1 billion to $2 billion a year of revenue. When we get to the elastic market, in this model, there would be $1 billion to $2 billion of revenue. If you try and lower the cost of access to space to $1,000 a pound or $500 a pound, revenue goes nearly to zero. Because the elasticity effect doesn't take off fast enough to use it. Right? And that bottom line problem means that you can't bridge this gap with private financing. Because no investor who has any brains will put money into this. You can't go to the existing industry. You can't go to ELA and say, lower the cost of $500 a pound by making a big investment. Because they say, oh, let's see, I'm making $1 million a year now. I'm going to invest $1 billion, and I'm going to come out the other side and I'm going to make $1 billion. Why not just continue to do what they do? So what he said in that study was these new markets require the development, the deployment and maintenance of large LEO infrastructure. That something has to drive that market, create that market. What might it do? Well, I started using, perhaps politically incorrectly, the term of affirmative action to describe what NASA needs to do to say to the marketplace, because I'm not sure we have a marketplace yet, but into the community and the industry. So things like ISS resupply is a first step. Propellant depots would be a huge and important step, and other people will talk about that today. Debris cleanup, and I think Joe will talk about that tomorrow. General exploration support, which was discussed by Joe last night. In the medium term, we need things like space tourism, but again, if it's 20 million a seat, there isn't very much of it. If it's a million a seat, there'll be a lot more, but if you're getting 2 million seats, it's going to be a challenge. We need the sovereign customers, is what Bigelow refers to them to move in. Maybe we need some big infrastructure projects like the installation of a number of tethers in lower orbit for exploration purposes, and Joe, I think, will touch on that in his other presentation. But the long term, as Jeff said, it has to be settlement. Nothing else works. It's resource exploitation tied to settlement. The challenge for us is bridging the gap. So quickly, roadblocks, technical. I don't think there are any breakthroughs. Bert and I disagree on this point, but fundamentally, we can make progress with breakthroughs, but we don't need them. Politically, we need an end to what I call cafeteria bullying. Some people are apparently surprised that NASA or that politicians want jobs in their own district. And people say, well, NASA could do so much better if X, Y, or Z. If it doesn't include, there are more jobs for Johnson Space Center or Kennedy or Marshall, it's a non-starter. Legally, I think we need sensible engineering and science-based regulation versus what I call emotional or fear-based regulation. And I'll just illustrate that by the fact that, when Spaceship One, before it took off, private jets came and landed on that field, including Richard Branson, the private jet, and so forth. No problem, just landed. Taxi, park. When Spaceship One took off, a truck had to go down the field to make sure there were no desert tortoises walking on the runway. Because that was part of the license requirement. Because it was a space launch, this versus grandfather under the Environmental Protection Act, airplane operation. This is ludicrous. But even more so is that when regulators think about disaster, their view of disaster is controlled by their field of view. So they look at a television image or a photograph of the Challenger, okay, or of a rocket exploding in the path. They don't realize that that's telephoto. It fills the screen, so it fills their consciousness. If you pull back and view that from 3 miles away, there's this little speck on the horizon that you might not even see. Okay, Challenger, you can put your thumb up and cover it. So the real question is, do we need the degree of regulation that's imposed? I'm much at odds with my colleagues in the industry on this, so all want to basically suck up to the FAA. I want to disestablish it. I'm on record in front of the Congressional Committee saying they should simply go away because they're not needed. But that's just me. To jump to social, I don't think there's any social breakthroughs that we need whatsoever. We've all been accustomed to and waiting for this since I first saw it in 2001 when I was in high school. Financially, we have a big problem. Okay, the problem is not whether or not we can raise money investor-wise. The problem is whether the dollar is going to be worth anything in 3 months. I know most of us focus on our technical issues, but fundamentally, the risk is global economic collapse. I've been a little bit of a doomsayer on this point for the last year, but I grow more and more worried. This is a very serious, deep structural problem that I'm not sure how to fix, short of something that makes a depression look like after markets, what other breakthroughs are needed? Well, obviously we need some risk capital. We need investment patience. This is a role for me. So being a libertarian, it's hard for me to say that, but again, this is part of this affirmative action problem. We need paradigm perceptual changes. Most of those have in fact now occurred. And just in the last year, the last decade certainly, but in the last year we've seen a fair number. There's what I call the mother-in-law problem, which is, you know, if you have a clever idea and you go looking for investment, you ask the investor, you know, how do I, you know, what do you need from me? You tell them, and yeah, they say, oh, let me think about this, and they call it the brother-in-law who, you know, was the second guidance control engineer for some subcontractor on the lunar module, and say, can this person do this? And they say, oh, that's crazy, you know, it took us 500,000 people and $24 billion in 1970 to make this happen. And so brother-in-laws have a lot to answer for. And in this particular case, I think they've definitely slowed down in the industry. We have a broken regulatory regime as far as I'm concerned. I don't want to get started about my term. But it's like taking a gun and putting it in your pants and pulling the trigger. Certain technological achievements would be nice, but they're not necessary. Things like your old TPS I mentioned, highly reusable engines, as well, talk about tethers. Some breakthroughs that I believe are utterly useless, and I don't have time to discuss some things like scramjets or really hypersonic, you know, in the sense that it is in fact true nonsense. Heavy lift will come when we need it. The traffic will. The technology I think that would be helpful is active cooling of structures rather than passive. We'll say, well, what happens if it fails? Burn up. Well, we see that passive systems fail as well as the case with Goff. But if you look at one of these guys, you know, if the active cooling of that fails, you have a problem. So, you know, we do active cooling on NASA right now. I see no reason why we can't do it on diesel. And everybody understands we need highly operable engines, companies like XCOR, others, and the small scale started to work on this. Certainly people have focused on it, but have never actually brought to market a truly highly operable engine that has thousands of flight cycles for reasonable cost. The solutions are, of course, reusable launch vehicles ultimately. This is where I spent most of my career. But as I say, it's a way to bend your pick more than once. Air launching is another option within the reusable set. I don't have time to talk about this, but I think that there's some very attractive options associated with that. Starting the company focused on that. And I think it's also a good match for Tether infrastructure as well. So what are the achievable price goals? So I'm going to go out on a limb and say, I think near-term vehicles that is well-designed receptacles or with partially recoverable components like engines and avionics could reach $500 a pound in as little as 5 years if you just start to develop now, just did. I think you could, in 15 years, reach $100 a pound. Now, my assumptions are that the R&D is pretty much amortized or moderated by grants, long-term loans, something to get to this point. And the thing that I talk about is manpower loading. It has to be business optimal. In other words, you have to staff as much as you need for the business and not politically optimal. In other words, building cafeterias. So my last slide is here's the take-home messages. Markets and flight rate control, they're what's enabling. I believe cash flow is needed more so than even investment. After all, it would be nice to actually make money doing this. I do think that some form of affirmative action is needed from the government to redress past wrongs in the business. I think improved engines and TPS would be desirable, but absolutely not required to concept exploration, refinement, architecture studies. Myself for T-Space and Dallas for Boeing back in the 2004-2005 time frame. He's a great thinker in the tradition of broad automobile hunter and others I could mention in terms of looking at the total architectures necessary for Cislunar space exploration and exploitation. I'm delighted that he was able to present that. And now I'd like to introduce Dallas Bienhoff of Boeing. Dallas is, we first sort of, I think, came to each other's attention when we were both running concept exploration, refinement, architecture studies. Myself for T-Space and Dallas for Boeing back in the 2004-2005 time frame. He's a great thinker in the tradition of broad automobile hunter and others I could mention in terms of looking at the total architectures necessary for Cislunar space exploration and exploitation. I'm delighted that he was able to present that.
Yeah. I was working on my master's at the time. So if we could have the PowerPoint slides that I gave you, Bill. What kind words to put me in those great people like Neil and Hunter and others. Thank you. Okay. So I don't have song and dance routines set up this morning. So you just have to suffer. So let me introduce Joe Carroll.
That is fuel depots also, though.
Pardon me?
Fuel depot and Tether go well together.
They do.
Tell us real quick what you do at Boeing.
Create the future is my standard one-liner. I work in advanced programs and deal with in-space and surface concepts for exploration, transportation, infrastructure, depots. And this, the story on this presentation goes all the way back to the release of the ESAS report and Mike Griffin's comments of if there were a depot there, we would use it. And we might even change our architecture. This particular architecture was devised during the Augustine panel Jeff Greason talked about. And so how do we get to the moon more frequently? And so these are the top 10 technologies for that architecture. So I'll talk about the architecture just to put it in context so you know what's driving the technologies. Talk about the top 10 technologies. What is the timeline if we follow the NASA budget, and what is the reasonable timeline to put in architecture like this in place, and how would that drive the technology developments? Talk about where would the NASA funding come from today based on the budget that's been passed, and then the technology impact of architecture and some of that. So this is a Cislunar transportation architecture that is enabled by depots. It is reusable. It is put in place with the ice miners that Jeff Greason mentioned this morning. Shackleton Energy Company, Jim Carroll is here representing them today. And that would move water back to LEO for use as propellants in Earth orbit. It was also put in place with Bigelow Aerospace in mind, and their far-reaching plans of putting habitats on the moon for the same reason they want to put their space stations in LEO, that is to lease them to sovereign countries. So you need a regular transportation system to get people back and forth and to get propellants back to the Earth. And what we have is a aero-captured transportation system that goes between LEO, the LEO depot, and L1. It moves the people and propellants and cargo up to L1. And then a space transportation vehicle that moves the goods from L1 to around the moon, which as it's passing by the moon, the lander drops off and goes down and lands. And on the return trip, it comes up from the moon and rendezvous with the transportation system to go back to L1. So we've broken up the propulsion steps into various stages to make it more efficient. And this was designed to move 25 tons from LEO to the lunar surface, because we can launch 25 tons today. And as a result, it can move 5 tons or 11 tons round trip. We've used 5 tons for the passenger compartment as an estimate for this. It does take twice as long to get to the moon this way as Apollo did. It takes 6 days. It takes 3 days to get to L1. It takes 3 days to get from L1 to the moon, roughly speaking. We can also move 25 tons back to LEO with the aero capture to get water into Earth orbit to be electrolyzed and made into propellant for sale by people who go to GEO, people who go on to exploration missions like the missions in Mars and so on. So that's what drives the top technologies. This is a closer look at the elements in here. We need personnel modules. We need a way to get propellant to orbit. That's that reusable propellant carrier you see there. The depot is in place. They hold 75 tons roughly in both LEO and L1. The space reusable transfer vehicle is all rocket that gets from L1 to the lunar vicinity. The aero capture that gets us back into Earth orbit on the way back without use of propellant, so we're using that propellant use. And then the lunar lander that gets us down to the surface and back up here. This is also put in place to use lunar propellants, so in the long run you can eventually reduce the amount of propellant that's needed to be launched and actually used. It drops the actual use of propellant for each mission by about 25%. So what are the top technologies for this architecture? Borrowing from David Letterman, with apologies. Number 10, in the long run, a variable mixture ratio of oxygen, hydrogen, space rocket engine. That will allow us to use all of the oxygen and hydrogen we get from electrolyzing water. So we can operate above, below, or at stoichiometric. Orbitech in Wisconsin does have an engine concept that they can operate stoichiometric. So, and they're operating at higher mixture ratios. So those technologies are in development today without government contracts. Low G and 0G liquefaction of the cryogens. We need to get that from gas and electrolytic process into cryogens and into tanks so they can be stored. We need to do that both on the lunar surface and in LEO. So we can transport water, much easier to transport water, lower volume, better temperatures than oxygen and hydrogen. Low G water electrolysis. I say low G because they already do electrolysis on space stations. So we've got that in hand, but we need to be able to do it on the moon. Show we can do it on the moon. Shouldn't be a problem, but it'd be good to show that, and it's a technology we need to have in hand. Number 7, deep space autonomous rendezvous method. We did Orbital Express. We Boeing and DARPA did Orbital Express in LEO. We had GPS at our disposal. In deep space, we won't have GPS, so it has to be able to find a target, capture a target, move up to a target, recognize it, and move in without prior knowledge of where each is from GPS. But they can communicate with each other. Again, we need to demonstrate that. That would enable the lander to come up and rendezvous with the transfer vehicle as it flies by the moon, would enable the assembly and operation of the depot in L1. Aero capture, obviously, if we're going to slow down using the atmosphere and LEO to save propellant, we need to demonstrate that technology. Back in the 80s, there was an aero capture flight experiment for the shuttle program that never flew. We need to revise that technology and bring that to bear. And you'll see where NASA had that in their plans in the proposed budget. Long life reusable engines. Gary Hudson mentioned this Earth orbit, Earth to orbit. We also need that in space. We don't want to be launching new systems every time we need to go to the moon. we're going quarterly or monthly, we need to have an engine that can operate for years on orbit, reliably and efficiently. Number 4, aero-assisted entry, descent, and landing. This is an enhancer to the propellant carrier to get us back down to Earth, to reuse it, expand the balloon. Maybe it's inflatable, maybe it's rigid, but it has to be collapsible in order to be launched efficiently and then provide a greater area on the entry process. Number 3, long-term zero-G cryogenic storage. This enables the depot and the use of cryogens and propulsion systems, transportation systems back and forth to the moon. Number 2, zero-G cryogenic fluid transfer. We need to be able to move liquid back and forth and not the gas. So we need to be able to separate the two in orbit and manage and know where the gas is and know where the liquid is in the tanks we're moving from and to. And then zero-G cryogenic fluid management, number 1. We need to be able to keep it cold. We need to be able to keep a liquid in orbit. As we replenish it, store it, not use it, hang on to it. And there have been some studies done in the 2005 year on advanced cryogenic stages that show we can get hydrogen losses down to about 0.1% a day. We need to demonstrate that. It's a nice paper study. It needs to be demonstrated and shown. And with cryocoolers, we can get that down to 0, which would be just great. So with the NASA budget, proposed budget from Obama, and we took the technologies that were in the proposed budget, this is kind of how this architecture might be developed. Whoops. We can pull AR&D, autonomous rendezvous docking from orbital express to do the depots and the tanker in orbit. The NASA FTD's flight technology demonstration missions had demonstrations that would also support that. It's a different technology than orbital express used. Cryostat was a depot demonstration mission, FTD-4. Aero-assisted descent and landing was a technology demonstration in the proposed budget. And all those just support these first 2 steps. The really important stuff for the implementation of the architecture is way out here in the 2025 time frame of the proposed budget. Kind of slow for a commercial activity or for something we need to support commercial activity. So that pushes all of these key elements for the infrastructure way beyond 2030. So what top technologies are not supported by the proposed budget? Number 10, the variable mixture ratio engine, liquefaction in LEO and the moon, water electrolysis on the moon. Number 7, deep space autonomous rendezvous and docking. And we also need that for missions to Mars and sample returns if we're going to use a split mission like we talked about. Long life reusable space rocket engines not in the proposed budget. So happily. And we'll get to the next one. So what are these technologies in a little more detail? What's long life to me? Unlimited starts and long operation, multi-year operations. What's deep space autonomous rendezvous? Locate and rendezvous without the use of GPS. Low G water electrolysis, disassociation into oxygen and hydrogen in the 1/6 and 1/3 gravity fields. Low G and zero G liquefaction, the same thing, converting those gases into liquids in those same gravity environments. Variable mixture ratio engines able to operate between mixture ratio 5 and 11, so that we have the right temperatures and can use all the water we produce as propellants. So here's a reasonable timeline to get an architecture like this in place. You need to put up an element a year, approximately, to get this done in a reasonable time period. And then that drives the timing of the technologies and when they need to be approached. What's needed now? The zero-G propellant cryogenic management, fluid management. Aero-assisted descent and landing next. Aero capture and long life engines. Deep space rendezvous, because now we can support the L1 depot. And then the low and zero G electrolysis, so we get use of water that we get from the mine, from the moon, and back to LEO, and make that into propellants. So where would this money come from in the budget that was passed? A little bit different than the budget that was proposed. There's only about $1 billion instead of $6 billion for the technologies, the 5 technologies that were in the budget. And that's over 3 years, so not 6 years. So we would have refueling and storage, in-space technologies, depots, in-situ resource utilization, a space transfer vehicle, technology and capabilities related to propulsion, and technology and capabilities related to ISRU. So these are the budget paragraphs where that money is located today, and it was authorized. Still not appropriated, so don't get your hopes up yet. I'm sure it'll be less. So what do these technologies do for us? Well, the first three enable the depots. Aerospace descent and landing enhances the reusable propellant carrier to propellant into orbit. Number 5, long life engines enables those operational efficient space transfer systems in space, aero capture vehicles, and the all rocket ones. And then aero capture for this architecture reduces the amount of propellant needed substantially, 7 tons for the aero capture vehicles, 21 tons for the crew transfer, and 1 ton, but it does add 1 ton mass penalty back to the systems for the aero capture mass and increase the propellant load for increased avionics. Deep space R&D, it enables that Earth Moon L1 depot and the ability to be made up in deep space without the use of GPS. And of course, the low G and zero G water electrolysis allows us to use water and transport water and convert it to propellants where we need it, not transport propellants around. And variable mixture ratio engines allows us to use all the water we get from the moon as propellants and not waste any. Some oxygen we'll use for people breathing, but they're not going to suck up all of that oxygen. We don't need that much relative to what engines need. So, propellant depots can allow us to greatly expand our capabilities. No matter how we get things into orbit, we can always do more. Whether they're small or large, propellant depots allow us to do more. These technologies enable us to establish reusable space systems. They enhance our reusable space systems' operational efficiencies by using propellant that's there, by using aero capture to decrease the amount of propellant we need to use to do our jobs. And they enable the oxygen and hydrogen propellant production from the water where we need it, not launching propellants from their original sources. And that's the end of my presentation. I'll have questions at the end. Gary?
We're going to switch over to Joe Carroll from Tether Applications. Most of you know Joe. He's been a tireless advocate of the value of tethers in space for 20 years, 28 years. I did mention that Dallas has got 36 years in the business, and I think I'm now at 41, so this is a pretty great. It's an old-timer session. So, Joe, come on up and talk to us. This is actually sort of a two-part presentation. Part one, we'll talk about tether slings in lower orbit, and part two, we'll talk about artificial gravity with tethers.
And actually, I snuck into more things, so.
Of course, he has.
Yeah. Notice the arc of the moon of the Earth at the bottom of these. I've been using this for the last 8 or 10 years as much as a reminder to myself as to my audience that I think that, at least when it comes to tethers, most of the action is going to be in relatively low Earth orbit. At that time, when I started doing this, I had colleagues who were fascinated with what you could do with tethers in low Jovian orbit and stuff like that, or low lunar orbit, or throwing things off the moon. Those are all possible, but I think that nothing ambitious is going to happen beyond low Earth orbit until similar analogous things happen in Earth orbit. So everything I'm going to be talking about, with one slide exception, is focused on LEO, but that one slide exception shows if you can do it in LEO, you can do it in a wide variety of other interesting places. So, we've got
fact that Dallas's and my 4 and his 10 ideas, there's no overlap. But my focus is a little bit different. It's not so much a large transportation system, but the first ingredient and one that, if it works, will change how you do some of the things. So the first one is not even space, but it may be the most critical thing for space, and that is radar capture multi-ton payloads. And I've got some videos. Then collecting and recycling aluminum in orbit. And there's a video segment of actually burning magnesium in dry ice. I don't know if you've ever seen this online video, but it gives you a new take on rocket engines using indigenous materials. Okay? Compressed Martian atmosphere can be an oxidizer. The third thing is high-altitude slings in LEO, and the fourth is an artificial gravity research facility. And this is based on the thesis that just as the French succeeded at the Suez Canal, which is basically just pure earth moving, but they failed at the Panama Canal because they didn't realize that it was really as much about mosquitoes and human disease patterns as it was about earth moving. And I think that successful human exploration is going to be as much about human reaction to hypogravity and cosmic rays as it is rocket technology. So I think that an artificial gravity research facility is going to turn out to be very important. So, wild card number 1. This was a test done by friends of mine 11 years ago. It was a capture of a 400-pound barrel of water by a helicopter. The parachute gets totally trashed in the operation. About the same time, colleagues of mine, as a subcontractor to me, did a mirror capture of a different kind. One person caught another, did not damage the chute. And the result of this was that he was able to release it, and the chute reinflated normally. Now, the guy at the bottom was wearing 3 chutes. He'll be happy to know. And then here's a top view of the second capture of 2 done in that subcontract. And it looks like that chute collapses suddenly, and it does, but the load transfer was very gradual. What happened is the captured chute was dragged forward, gradually reducing its lift coefficient until it collapsed when it approached 0. So John LeBlanc, the guy who did the capturing, when he got down to the ground, he called me from the landing zone and was all excited about the fact that there was no jerk load whatsoever. Okay, that he grabbed the guy with his feet. It was just very smooth transfer over several seconds. So now, this is all small size stuff, but if you can capture stuff with no snatch loads or low snatch loads, and without damaging the chute, that makes mid-air capture a different ballgame. Instead of each capture test costing you a chute, you can do 10 or 20 parachute captures in one flight test. You can get an order of magnitude more practice for less money, okay? And the fact that you can do this with a variety of techniques that not necessarily involving radar chutes, there are other gliding chutes, ground chute concepts, or even some concepts that don't involve parachutes. Okay? So why consider mid-air capture again? Okay? It allows downrange booster recovery without water impact or intrusion and return to the launch site within hours. And the question of if things get really cheap, my rough guess is that the cost, that incremental cost of recovering a first stage booster downrange from a big helicopter is of order $10 a pound. So even when launch costs are $100 a pound, you can still afford to do this kind of thing. Okay? If you're using, I gave this slide earlier this week in a group in this room actually involving the Air Force, and they're all fascinated with glide back and rocket back first stages. And I pointed out that if you recover downrange, you don't need as much of a glider performance. Okay? And then one of the other things is if you've got a downrange abort, if you've got a helicopter there that can recover a first stage, the first stage always weighs several times more than the payload in any vehicle design I've seen. And that means that you can recover the payload instead. Okay? So there's some very interesting things. I think this is the highest leverage tether technology, and in fact, the highest leverage technology for next-gen rockets. Okay? Is there anything new? Capture without chute damage, capture of large gliders, allows towback.
okay? You don't need a parachute. If you have something that isn't glider, you can come and grab it, kind of like a mid-air refueling contact, except you don't need hoses, you just need ropes. You can drag it back. Plausible limits for a conventional carryback of a slung load with a helicopter. The CH-53E has a rated external tow carrying capacity of 36,000 pounds. I wouldn't try to go all the way to that, but I think you can go to most of that, okay? That allows relatively substantial, not quite EELB class, but something smaller than that. And perhaps 100 to 200,000 pounds is the limit if you go with some kind of glider towback where you rendezvous, grab it, and drag it back. Now, what are the implications? If this substantially improves cost effectiveness by allowing recovery from downrange of a first stage, then boosters too heavy to capture may not make much sense. When you look at just gross, pounds, dollars per pound for propellant delivery, a lot of small missions may be cheaper than a few big ones if the small missions can do no damage first stage recovery. Okay? And then here's the real conundrum for developers. If this may seriously improve cost effectiveness, then maybe you need to find out if that's the case. Maybe you need to focus on this first before you sit down and try to design a rocket. I think that if there was any part of my presentation earlier this week that gave the Air Force heartburn, it was probably the idea that the most critical technology for rockets is parachutes and helicopters. Okay? I think the Army might like that better than the Air Force. Okay, wild card 2. And by the way, a friend of mine, a mentor, Jim Arnold, who used to be, was sitting in his office at Scripps Institution of Oceanography 40 years ago, and the director of research, John Isaacs, a famous creative thinker, walked into his office. He says, Jim, I just realized that when the Columbia River mixes with the Pacific Ocean, the mixing of the fresh water and salt water wastes of free energy that's greater than all of the energy that we harvest in the dams of the Columbia. Now, Jim, if you're a smart chemist, you'd figure out how to use that. And then he walked out of the room. Okay. There actually, I just found out earlier this week, there are companies that are working on that now, as a power harvesting concept. This is one in that category, okay, collecting and recycling aluminum, and in particular, learning how to make liquid aluminum fueled rocket engines. We have solid. Most people don't realize this shuttle burns more aluminum than hydrogen on each mission. Okay. Aluminum is rocket fuel. So why consider recycling? The debris in low Earth orbit weighs over 2,100 tons. That's just about exactly the weight of a shuttle fully loaded on the pad. Okay? That's already in orbit. Okay? And probably over 1,000 tons of that is recoverable aluminum alloys. And most future stages, the Air Force's current design, the idea they're in love with is a recoverable first stage and a throwaway second stage. That throwaway second stage weighs about as much as a payload. If most of that is aluminum alloys or other recoverable media, and you can reuse that, you have double your throughput to LEO. Okay? So this is not a small effect. Second thing is controlled vapor and molten spray deposition on hollow forms can give you better metal properties, a better combination of ductility and yield strength than you can get from ingot metallurgy, conventional metallurgy. And it also allows direct fabrication of arbitrarily large structures. We tend to think of a factory as something like this that makes beer cans like this. Space manufacturing is going to become things like this, making things like this. Okay? Doesn't have to do it in a hurry, but it doesn't have to make 1 million beer cans. Okay? There are 2,500 objects. The 2,100 tons is 2,500 objects. Okay? They average a little under a ton each. If you were to process one a week, okay, chewing it up, that's good. So, and here, for this conference, if there's anything that's important in this slide, it's the third one, the third bullet, barely extraterrestrial materials. I don't think we're going to be recycling, doing stuff with with water and breaking rocks on the boom or in free fall. Okay? And it is more challenging, it's time critical, there are all sorts of unconventional problems with it. However, there are very unconventional payoffs as well. Okay? And the one thing I don't say here that I should mention is a lot of people have tried to extend the capture window to make it more like a free fall docking. Forget about it. Okay? The time to know on your errors is during minutes of approach, not during seconds of panic. Okay? Carriers don't come and hover over carrier decks. If there's a possibility of landing in a conventional air, you know, it's just aircraft landing in carriers, you abort if you can't do it safely. Okay? You have much more time. You don't have side winds or gusts to worry about in space. Okay? Now, rotating slings versus vertical elevators. And vertical elevators can include both the things connected to the ground, the conventional space elevator, and also if you take a chunk out of a space elevator, it could be orbiting, and it doesn't need to be geosynchronous. It could be a vertical tether that's 1,000 kilometers long in low Earth orbit, and the lower end is substantially less in orbit velocity, just like with a sling. It's a longer tether, and it has the disadvantage that if you get captured by wind and you can't easily get to the other, you have to climb. You can't just wait for half a turn and let go. Slings have a tremendous advantage in going beyond LEO. Vertical elevators, after debris is cleaned up, appear to have an advantage if you want to maybe have, you know, kind of like the ultimate space transportation hub in the sky, where you go up and have your expensive conference here in partial gravity, with down being down, as opposed to a sling where you're spinning and you don't really want to look out the window. But if the main market is people to and from LEO, you want a vertical elevator probably. If it's a lot of payload going beyond LEO, rotating sling is probably the way to go. Now, here's the real challenge. Many of you folks are somewhat aware of tethers and slings. I want to be cautionary here, okay? There are different analogies you can make. Rockets are like ships, okay? There's a port, and then once you leave the port, you can head in any direction, okay? That's not true with railroads. Railroads ease repetitive transport along a certain route, okay? And it's not just specific destinations. Anywhere along that route, you can stop, okay? You can stop in the middle of nowhere, but only on the railroad track. This is a real constraint. It is particularly a constraint to the military that does not want to be constrained as to where it goes. Okay, but for manned space, you're probably going to be going to a destination. Okay, and so being constrained to one or a few inclinations may not be a problem. I'm not going to go into all 9 of these, but the first 3 I will go into, and all 9 are here so you can look at it in the presentation after the conference. The first one I've already referred to, okay, going by the way, the orbit plane constrains ops. Okay? And let me get more specific. Here are the candidate orbits that make sense to me. Okay? One could also argue for 34 degrees as an inclination and land in Bermuda for the first stage taking off from Florida or Wallace. But that's a bit far for most first stages. 51.6 has a lot of attractive features. It can serve nearly all orbital launch sites worldwide, and it might capture some or most manned space business. I happen to think that nearly all manned flights in the next 30 years to orbit are going to go to 51.6 orbit. Okay. There's a paper that I can include in the proceedings that has a 3-page appendix arguing that point. Okay. 28.5, you get 7% higher payload. Wow. Okay, 20% with RLVs. Okay, they weigh a lot more than the payload, so the marginal cost of higher delta V is much higher with RLVs. Then there's 0. Okay, but I don't know that there's any other plausible inclination for a sling. The real payout for zero is geo traffic, including power sats. Okay, I think the first sling is going to be at 51.6, and the second one is going to be a bigger one at 0. Okay. If this happens at all. Somewhere
for Spaceship 2, Spaceship 1, Spaceship 2, Lynx, etc., the higher you fly, the further you fall, and the harder you run into that atmosphere. And when you fly twice as high and fall twice as far, it would be nice if the atmosphere was spread out so that you could decelerate over twice as much a height. And actually, Reusable does a little bit of that because with his reconfigurable shape, you can actually change his ballistic coefficient during the pullout. But suborbital entry is different from orbital. Orbital, you can do just enough of a deorbit that you graze the atmosphere. The shuttle actually, even if the Earth's atmosphere weren't there when the shuttle deorbits, it would just be in a low orbit. The perigee is about 40 kilometers. And so it's tiptoeing out, flaring, even before it starts its aerodynamic flare. That makes it soft and reduces the peak heating and the PG loads. If you're significantly suborbital, and you let go from shuttle altitudes, space station altitudes, it's going to be slammed re-entry. It's going to be high peak Gs, high peak heating. So you really want to let go from as low an altitude as possible if the re-entry is suborbital. And that includes abort to orbit, a late abort, where you try to capture the chassis and can't. Okay, you have to be able to plan to survive that. You want that to be gentle as well. And what it really boils down to is tether, heating, drag, and dynamics are problems. All of them begin to be problems around the 100 to 130 kilometer region. So you want to be right about there when you let go. So the tether has to reach down to that. Okay? And here's the real problem when you combine with that you want to capture low altitude, that you lose altitude after you capture. Okay? There are ways around this. 2-1 resonance, elliptical orbit, there may be other magic things that you could patent. Okay? But you have to solve this problem that after you grab a suborbital object, one turn later, you don't toast it and your tether. Bottom line, what might a Sling look like? I don't have the time to go through all of this, but this is a study that I did actually 19 years ago for Becky at NASA headquarters. NASA actually paid attention to most of my ideas until I succeeded with 4 flights in the early 90s, and then they changed the personnel I was dealing with and stopped listening to me, so I don't know what the story is. But this is just, okay, this is the Earth. This is, reaching down 3/4 of the way to the ground. This is 10-second intervals of the Sling and the launch vehicle. It reaches MECO about 100 seconds before capture and coasts, and it has that 100 seconds to fine-tune its trajectory, and it gets just barely outside the atmosphere. And if you want to play kind of pack rat, where you grab one and you let go of another, you can have either the aborted vehicle land here or the returning vehicle land here. Okay, that simplifies the dynamics. It's a serious constraint, but it's one way of solving the altitude problem. Are we ready for a railroad here? There are real constraints, but there are large payoffs. Okay. Implications of works better with small payloads. Rail cars are substantial compared to trucks. They can handle higher payloads. But those payloads are tiny compared to ships. Rockets are like ships. Tethers and slings are like railroads. You're going to optimize out at more frequent traffic and smaller payloads. Okay? And only fixed routes. Okay? It does encourage two-way traffic. You want to harvest that momentum, you loan your payload. Okay? Slings and rockets designed for the slings depend on each other. You've got a real problem where nobody wants to, Elon doesn't want to depend on Bob Bigelow succeeding, and Bob doesn't want to depend on Elon. He'd like it to happen, but he doesn't want to be totally dependent on it. Well, here you've got a similar problem with slings and rockets designed for him. Is it going to be one big company, and then that one big company has a monopoly? These are issues you have to think about. Now, this is shifting gears. This is from transportation to why would you do something. Okay? And this is something that NASA hasn't funded at all. I think in general, when somebody says, oh, I've got this neat idea for an artificial gravity facility, NASA says, wait a second. Our brand is microgravity. I've never had anybody actually tell me that, but I have a feeling that that's the mindset, okay? So I think this is going to happen for a variety of reasons, more in spite of NASA than because of NASA. Okay, this is not a criticism of NASA, this is human self-interest of the same sort that we have here today in this room, okay? But I think that there are important things that, as I mentioned earlier, Panama Canal turned out to be as much about mosquitoes as about earth moving. Human exploration, settlement on the moon and Mars is going to have to do as much with human physiology and even plant physiology. Okay, we're not going to be living there until we can grow at least a lot of our own food. Okay. We don't know what plants are going to work well in partial gravity. Okay. And what changes in biology they're going to have and gene expression, what their nutritional effects will be. We don't know whether, as it is now, mice in microgravity cannot reproduce normally. Okay, various steps in the process work, but implantation apparently doesn't. We don't know what the future of man is at partial gravity in this important respect. Okay, or we do it with people. And one of the powerful arguments in my mind for this being a commercial facility rather than a government facility is that the first pregnancy should not involve government employees or government facilities. Okay? Now, I think these top 5 are really important issues. These are the kinds of things that people have worried about. If you worry these, somebody that does that can answer these questions as well. Now, you notice I have this dumbbell. It's a spinning dumbbell. The arrows here. Here. It's a spinning dumbbell. But besides the asymmetrical end masses for Mars and Moon, there are 2 inward nodes. Well, there's a center of mass node to allow conventional free fall rendezvous. Okay? It turns out the trapeze capture is difficult, or it's difficult for some vehicles but not others. Make the rendezvous with the center is. I've also added a 0.06G node, and there are actually a couple different reasons for it. Neil Pellis at NASA JSC, who's been head of the biotech program, has been on and then off and now maybe on again. He says that 1/E steps in gravity level look like a very good step size for doing experiments to find out where the thresholds are. It'd be nice to have a knob to turn the gravity up and down arbitrarily, but then you got to do a whole bunch of experiments after the other. Start with some decently spaced steps. And rather surprisingly and conveniently, Mars is just about 1/E of Earth gravity, and the Moon is just about 1/E of Mars gravity. Okay, it's not exact, but it's like within 10 or 20%. The next step below lunar gravity, 1/E, is 0.06G. And I've done a number of experiments that are very crude and simple, but such things as sitting in a swimming pool on the steps at different levels of different parts of your body out of the water, so different amounts of weight pushing you into the seat. You find that if you don't have enough of your body out of the water, you can't even sit normally because your muscle tension pushes you out of the chair. Okay? In addition, rolling over in bed below some gravity level, you're going to just continue gracefully arcing on the floor. Okay? I tend to think that around 0.06G is going to be the lowest level that people will intuitively adapt to, not need a 0.10G adaptation phase, and it may be that people end up commuting in this facility and doing a lot of their playing here. They're eating and going to the bathroom here, and maybe they're sleeping here. Okay? And I don't think that they're going to be uncomfortable except right near here. Okay? This is all guesswork, but I think that the problems with gravity have to do with when it disappears and the otoliths are floating. Okay, not so much there's less pressure on it, but again, I'm not an expert in this, I don't know for sure. But we can test it and talk about that a little bit. So the basic concept, the problem is we don't know how long this has to be. There have been a bunch of rotating room experiments done in the 60s, actually the Grayfield Laboratory in Florida. But John Charles at NASA JSC, head of the bioastronautics program, bioastronautics roadmap, he says that he is very worried spinning this way. And when you're spinning this way, as you would in an artificial gravity facility, if you walk against the spin, you get lighter. You turn around, you walk with the spin, you get heavier. You stand up, you tilt to one side if you're facing one way, the other side if you're facing the other way. They found that people could, in the Greason tests, that people could adapt to multi-RPM spins over time. But the problem is that when you're standing this way, you're spinning like this, and then you turn around, you're all of a sudden spinning the other way. And if it's like 1 RPM is the threshold for immediate, adaptation problems, well, here there's a 2 RPM change. Okay. Cabin layout options. There are a variety of different options. The one I tend to like is a 12-foot diameter, and so I show that in the rest, but the other two are also feasible. Here's the Falcon 9 base cabin that's based on the first stage. The 12-foot rocket diameter is continued and stretched to the point where the bending loads during descent, maximum bending loads, would be similar to that of the shorter batted standard Carroll. Well, this tank here is about the same size as a 737-600 cabin. That's substantial. Okay. Here's the potential radial structure. If you don't have to make the thing miles long to keep the spin rate low enough, you may be able to use something like this. This is the same folks that did the first mid-air capture did this. Okay, there's 85 feet span here. This is Roy Haggard's car, a friend of mine in Lake Elsinore. And when this is not supporting the car, 2 people can pick it up and move it. Okay. You can very easily make a half-kilometer to kilometer-long tunnel that allows people to take an elevator between the different levels. So these are the kind of things that you can get. If it's a short enough structure, if we find out that we can do it with short structure, rigid modules. If it's longer, it wants to be tunnels. If it's very long, it wants to be tunnels on this side and cables on this side. And in that case, the 6G node is moved to this side so that you can access it by tunnel. We don't know which one we need to do, but here's how to find out. This is the Soyuz, okay, Soyuz spacecraft. This is the spent stage that takes it to orbit. It weighs 1/3 as much. You have a 600 meter tether, about 20 kilos. You can spin up using thrusting from the heavier end, which is not the best end, but you can use some of your phasing, at end of phasing propellant early to spin you up, and then let go later, and all that energy you've added, if you let go, this is on the top, all that energy stays in the stage. But you can do tests at various RPMs and G levels to find out if a certain combination of spin rate and gravity is tolerable. Okay? This can be done on any mission to the space station. The analogous mission on Gemini 11 was done in less than a year from when it was first proposed. Okay, this could be similarly done in less than a year, if there was an interest. Full development, you can stare at this later, and again, there's a paper on this that's 22 pages that I'll make available. There are 2 operational derivatives, okay? One is the spinning cruise stage, and the other is the high altitude Sling, okay? Conclusions for this wild card. We've been going in orbit for almost 50 years, but we seem stuck. Okay, maybe it's time to take human physiology seriously before planning long missions. So Micro-G was fine for Apollo, but it's not going to be fine for trips to Mars. Okay? And it's not going to be available when we're trying to live on the moon and Mars. I mean, artificial gravity facility lets us learn more about our future and limits on the future and test ways around those limits. Okay? Right now, the full focus of the countermeasures is trying to make the crew not be boneless chickens on the way to and from Mars. Here, the point of the countermeasures program is to find out what kind of future humanity has off planet. That's a lot more important. And we can start with this, the Tether, Soyuz, or Dragon test if it's not done real soon. Recap the wild cards. I'll be here through the rest of the conference, and I'll be talking in more detail about collecting and recycling aluminum tomorrow. We have about 12, 15 minutes for questions. If you use this mic, because it's the live one, just line up and at it.
When is the first mistress? After the book of the Canadians realize that they're straining their civilization by shooting on Mars Earth. And every time I see the propellant from Mars, I get the sinking feeling within my stomach, and I get my throat to really screwed up. I'm wondering if maybe there's an alternative. There have been people who have talked about accelerating lunar iron using its magnetic properties, which of course would be a lot easier to store. But I've never heard of any idea that that actually work.
Not a clue.
It's several percent. I can't recall all that the iron, free iron level. There is free iron that you can separate from the magnet. Yeah, and the thing is, the free iron, you can accelerate things that aren't all iron. You just use iron as, you know, part of that element.
Texas economic development office, the state of Texas level, on the idea of penalty goes to space. There's a lot less work than that. You speculate on non-federal government sources of capital in development space.
If there's a customer and money to be made, there'll be money to be lent. That's about as far as I can go.
Yeah, I'll make another comment. That is, until we fix ITAR by returning to something close to the 399 status, there will be no commercial projects involving the U.S. and other countries that are substantial. For example, this artificial gravity facility, it'll be commercial. If ITAR is fixed, it'll probably be a U.S.-led project. If ITAR is not seriously fixed, it'll be a foreign project with the U.S. as customers. Period.
I was also going to say there is potential for starting to get a toehold on some space infrastructure projects commercially. I mean, there are needs out there. It's just they're very hard nuts to crack. We've got to keep the initial capital levels low enough that when you need $100 million to do a project, it's a lot harder to find that capital than if you can keep it in chunks that are low enough that you can use an angel investor that may be investing more because they believe in the idea than necessarily because it's the best investment compared to like investing in another big company or something.
The so-called adventure capitalists.
Yes. Yes.
Pete?
Yeah, Keith Benson. Way back, 77 or 79, I guess 77, Eric Greason and I worked out a vapor phase fabrication. And in there we came up with an interesting metric for it, which is really the time that it takes for an aluminum boiler, solar-powered aluminum boiler, to boil its own weight per liter. And it turns out that if you want to recheck that, the number we got was 8 hours.
It's likely to be, and it really doesn't matter whether it's 8 hours or 8 days, it just doesn't want to be 8 years.
Yes. We didn't force it at all. Just turned out to be.
Yeah, when it's 8 hours or 8 days, your real costs lie elsewhere in the system.
Yes. It's not, it has a very high productivity. And the other thing I was a bit surprised about is that there's no mention in your thing about tethers of the lunar tether approach.
Again, I started out with LEO, but the picture that had Earth, Moon, etc. Once you do it in LEO, you can do, then you will start to have a market to do the same thing elsewhere.
I reworked it with Jerome Pearson worked it.
Yeah.
And it turns out that a tether will lift about 1/65th of its own weight per day. So a 65,000 ton tether that's mostly weight, like 19,000 tons.
Every system, whether it's rockets or tethers, will pay off if there's enough market.
Right. But it's fairly cheap to do this. As a matter of fact, it is so much easier than putting a power plant on the lunar surface and that surprises me is that hasn't completely replaced the ideas that many other ideas of getting stuff off the lunar surface.
Next.
Very hard. Looking at the drivers and balances describing challenges, if you will, for construction. With respect to not having GPS, one of the proposals in the report that someday will make it out of NASA headquarters is for a commercial Cislunar GPS infrastructure investment, which will make that one go away. The second one is back in the early 70s, Bienhoff was built a resistive jet test bed because they figured someday somebody was going to find a situation where we're going to need, maybe if we're going to Mars or somewhere in terms of dealing with near orbit issues, there's going to be fluids, and maybe you have a restartable engine that could just about anything you could throw out. The more energy you get, better you, more bang you get for your buck. Why wouldn't we consider something like that versus insisting that we have Shangri-La with cryogenics from the start?
Thrust levels, primarily.
This takes longer.
Right, and the longer it takes, the more infrastructure you need, the higher cost you drive in the system, and the more assets you need in order to do the same job, the same throughput.
Yeah. We have limited time, so let's try one question and answer.
I just wanted to make a comment. Kudos to you, Joe. I'm Jim Logan, Senior Flight Surgeon at JC, and it was the best summary of the absolute need to do the studies for artificial gravity from a non-life science person that I've ever worked with.
Thanks.
I have looked at 50 years of spaceflight data. Next year will be year 50 of human spaceflight. We know two things. Number one gravity, 24 hours a day, 7 days a week, works. Number two, zero gravity, 24 hours a day, 7 days a week, does not work. Until we do the studies that you talked about, which was very articulately communicated, it is very likely that the moon and Mars, even though they may be sortie destinations, will never be civilization frontier settlements.
Yeah, I realized just a couple days ago that this facility will remain in use after there are settlements on the Moon and Mars, because the ease of doing diagnostic, quick feedback studies with return of crude blood samples, et cetera, to the ground will remain. It'll actually have more value after we have a real settlement than before.
Absolutely. And in addition to your excellent example of the Panama Canal, first circumnavigation of the globe was a lot more about nutrition than it was about seamanship.
Yeah.
Let me mention trouble, including preservation of space resources.
By the way, packing for Mars, read it. Okay? I'm sure that every NASA manager is rolling. You've probably been criticized, John Charles' blog has probably criticized. All the NASA people quoted in that book have probably been criticized and taken to the woodshed. But it's a great summary of the problems.
Having been taken to the woodshed many times during the 19 years of NASA, I assure you that they probably will survive.
Yeah, great. Thanks. Okay. My one cautionary note is there are many issues with the solid oxides and volatiles. You want to include volatiles, and aluminum is volatile as you like. And the final thing is we have to restrict where they're used. My suspicion is that most of the small debris in low Earth orbit is not paint flakes, as was originally thought, but it's the result of using aluminized solid upper stages at altitudes beyond where they should be tolerated. It's okay to use them at 200 kilometers. It's not okay to use them at 600.
I would like to raise a question. You
agree with the whole idea of working with the world. I agree. However, reluctantly, we can help the government. The question is, how can we organise what the government? It seems to me that ever since the past, the NASA human spaceflight program has consisted of two kinds of projects. One is long-term regular projects actually going like the Hudson on the space station, and the other is ambitious projects proposed by some president whose defining characteristic is they don't cost much money until the next president's. Well,
That's competition's pattern.
the next president, of course, cancels it in favor of his ambitious project. The cost being shoved off in the future again. You have to get through that, I think, and it seems to me the way to get through it is to try and limit NASA to doing things which are short term. Things like making reusable rocket engines. Instead of having great ambitious projects, let them go explore if they want. The great deal of the effort in human spaceflight by NASA seems to me should be on things which are definitely going to get done in less than 8 years.
Well, I think that, going back to what I said about markets, if we can use them to anchor a couple of initial markets, frankly, it doesn't matter whether it ever amounts to anything. Okay, I mean, it could be to put sand as well. Sand is a bad choice. Water in orbit. As long as it drives that initial market, they will have served a useful purpose.
In NASA, it doesn't matter. NASA has probably more control over its own long-term direction than any other federal agency. Except what?
DARPA.
Except DARPA, yeah.
That's
and they don't really care what they do as long as they look good at doing it and therefore keep getting funded. And I think the answer to the question about what to do with NASA is you have to figure out how to retread each center to do something useful. And half of them may be, energy or climate change or whatever, not getting in the way of space.
Well, I will leave you with one thought. Back in, I think it was 1921, might have been later, it might have been 28. A count whose name now I cannot recall was asked by a German newspaperman exactly what needed to be done to move on with all this interplanetary flight talk, which was Fritz Lang and Carroll and so on. And he thought for a moment, he said, well, there are three things. First, find the money. Second, get the right people working on the job. Third, get the wrong people off the job. With that, thank you all, the presenters of the session. I'm honored that they accepted the invitation. Thanks very much.
It is now time for our coffee break and networking. I have a further announcement. Ron asks me to inform you that if you have a bill for Wi-Fi from Carroll, refuse to pay it, it's your comp. That's it. See you back in about 15 minutes.